capacitors also store energy. When we draw the capacitor with its voltage and its field and its charge, we think of it as storing charge, and it does store charge. But a lot of times sort of the point of a capacitor is to store energy in a circuit. But let's be clear, but not enough to replace batteries. In terms of long-term storage, capacitors are a problem. They kind of leak. You may have noticed our little voltage went down in time a little bit during our demo. Well, they do make fancier capacitors than that. But they do leak, and it's just hard to get enough charge in there. You can read about supercapacitors. That's an effort to get as much energy as we can in capacitors, because they deliver the energy very fast, much faster than a battery can, but they can't hold nearly as much. So let's think about this. How do they store energy? How much energy do they store? So I'm going to draw a capacitor here, and I'm going to draw it getting a little bit into what it really looks like. Here's the metal wire that comes to the capacitor, and here's the other plate here. Other metal plate like that. It's starting to look like a real circuit element. And if we charge it up, we put some positive charges on that plane and some negative charges on that plane. So it has some capacitance C and it has some delta V. Okay? So the question is, how much energy? Which I'll call U. How much potential energy is in there? So you might look at it and you think back to our learning sequence on potential, and you'd say, well, if you have a charge Q at some potential, then that's the energy. You just multiply the potential times the energy. So you might say U is just Q times delta V, right? And then say, well, Q from what capacitance is C times delta V. So that is that times delta V. It's just bringing that down. So you might say it's C delta V squared. Right? And you would be wrong. It's not C delta V squared. No, it's not C delta V squared. I worry about writing incorrect equations. That's why I instantly scratched it out. It's not that. And here's the reason. It is true. You have a charge Q at some potential V. But when you put the charges there and you did the work to put the charges there, it wasn't at delta V. When you put the very first charge on there, the delta V was 0. It was just two neutral plates. Right? So when you add charge, you build up the delta V. It wasn't there the whole time. So what you have to do to see it build up, let's watch the charge build up and think about it. So what we have to do is think about differentials. What little bit of energy du do we get when we add a little dq? Well, it depends on what delta V was at that time. Okay? So delta V here is a function. It's a function of how much charge is on the plate. So each charge you add will add some energy. How much? Whatever delta V is. If it's 0, it won't add any charge. So let's now put in the function and integrate. Okay? So we're going to integrate both sides. That's just going to give us U, the total energy. The function, delta V, is Q over C. It's how much Q you have, how much charge is on it over its capacitance. And I went to Q because I have a dq here. Okay. And we're building up the charge all the way from 0 to big Q, the amount of charge on the capacitor. There you go. So do this integral, and it's equal to 1/2 1 over 2c q squared over 2c, if you do that integral, evaluated from 0 to big Q, like that. Of course, the 0 gives you 0, so you get that the energy is q squared over 2c. And if you want to, you can write the Q as C delta V, C delta V squared over 2c, and then you get, let's see, that c cancels one of those, you get 1/2 c delta V squared, if you want to do it in the same terms as you did over here. So it's not c v delta V squared, it's 1/2 c delta V squared. And the factor of 1/2 is because the potential had to build up over time.